Hello guys, today we are going to be discussing about equations reducible to the linear form, or we call them Bernoulli equations. So any equation of the form dy dx plus py is equal to qy raised to the power of n, where p and q are constants or functions of x, can be reduced to the linear form on dividing both sides of the equation by y raised to the power of n and substituting 1 divided by y raised to the power n minus 1 to be equal to z. So we can show this as follows. So we have here our dy dx plus py is equal to qy raised to the power of n. Note that in the normal linear form that we know, dy dx plus py is equal to q without this y raised to the power n multiplying it. But for Bernoulli equations, they always come in this form: dy dx plus py is equal to qy raised to the power of n. So on dividing through by y raised to the power n, we have 1 over y raised to the power n dy dx plus 1 divided by y raised to the power n minus 1. Using the laws of indices there, y raised to the power 1 divided by y raised to the power n. We have 1 divided by y raised to the power n minus 1 into brackets p, multiplied by p is equal to q, because we've divided this by y raised to the power n too. So now on substituting z as 1 over y raised to the power n minus 1, we have dz dx to be equal to 1 minus n divided by y raised to the power n multiplied by dy dx. And as such, we can make our dy dx the subject of formula in this equation. So we have our dy dx to be equal to y raised to the power of n divided by 1 minus n multiplied by dz dx. So let's take a look at what follows. So we have 1 over y raised to the power n multiplied by dy dx plus 1 over y raised to the power n minus 1 multiplied by p is equal to q. Since we've made dy dx the subject of formula in the previous equation, we know that 1 over y raised to the power n into brackets y raised to the power n divided by 1 minus n multiplied by dz dx plus zp, because z is now 1 over y raised to the power n minus 1, must be equal to q. So on simplification, we have dz dx multiplied by 1 over 1 minus n plus zp is equal to q. So we can multiply all through by 1 minus n to get dz dx plus p multiplied by 1 minus n multiplied by z is equal to q into brackets 1 minus n. So now this looks like the general form for the first order linear differential equation, which we can now solve using the method we described in the previous video. We said the first thing is to express it in terms of the linear form, which is what we've just done. Then we'll find the integrating factor, after which we then find the general solution using the formula given in the previous video. Now let's take a look at this first example. We have x squared dy plus y into brackets x plus y dx is equal to 0. So to solve this, the first thing is we have to express it explicitly. So we have our solution. We now have our dy dx plus y into brackets x plus y divided by x squared is equal to 0. So we can simplify this to give dy dx plus xy plus y squared divided by x squared to give us 0. So our dy dx plus xy divided by x squared plus y squared divided by x squared is equal to 0. So our dy dx plus y over x will now be equal to minus y squared divided by x squared. Now this looks like the general form of the Bernoulli equation, which is dy dx plus py is equal to qy raised to the power of n. So in this case, you can see now that our n is equal to 2. Let's go ahead to simplify it further. So we have dy dx plus y over x is equal to minus y squared divided by x squared. So on dividing all through by y raised to power 2, we now have 1 divided by y squared dy dx plus y divided by xy squared to be equal to minus y squared divided by x squared y squared. You can simplify this to become 1 divided by y squared dy dx plus 1 all over y x is equal to minus 1 divided by x squared. Let z be equal to 1 divided by y raised to power n minus 1. Now, in this case, our n minus 1 is 2. So, it is 1 divided by y raised to power 2 minus 1, and that's 1 divided by y. So, now we know that our dz dx is equal to 1 minus n divided by y raised to the power of n multiplied by dy dx on differentiating implicitly. So on substituting n is equal to 2, we have our dz dx to be minus 1 over y squared dy dx. So dy dx now becomes minus y squared dz dx. So we could have eliminated the minus sign in front of the y by making z to be equal to minus 1 divided by y raised by n minus 1. So that makes it easier, and in subsequent examples, we are going to be making that substitution instead. So now we have 1 over y squared dy dx plus 1 over xy is equal to minus 1 over x squared. We can substitute our value of dy dx to give minus y squared divided by y squared dz dx plus 1 divided by xy is equal to minus 1 divided by x squared. So we have minus dz dx plus 1 over y x is equal to minus 1 over x squared. Now recall that we said z is equal to 1 over y. Hence, we have minus dz dx plus z over x is equal to minus 1 divided by x squared. So we can multiply all through by minus 1 to get dz dx minus z over x to be equal to 1 divided by x squared. So this now looks like the general form of the first order linear differential equation. So now we have dz dx minus z all over x is equal to 1 over x squared. Now we have our p to be equal to minus 1 over x, and our q is equal to 1 divided by x squared. So the next thing is we find our integrating factor. Our integrating factor is now e raised to power integral of p dx, which is e raised to power integral of minus 1 over x dx, which is e raised to power minus integral of 1 over x dx. So our integrating factor is now equal to e raised to power minus ln x, which is equal to e raised to power ln 1 over x. Our integrating factor becomes 1 over x. So our solution is y multiplied by the integrating factor is equal to the integral of q multiplied by the integrating factor with respect to x plus c. So we have y multiplied by 1 over x is equal to the integral of 1 over x squared multiplied by 1 over x with respect to x plus c. So we have y divided by x is equal to the integral of 1 divided by x cubed with respect to x plus c. And this gives us integral of x raised to power minus 3 with respect to x plus c. So y divided by x now becomes x raised to power minus 2 divided by minus 2 plus c. Our y over x is now equal to minus x raised power minus 2 divided by 2 plus c. So I just realized that our solution should be in terms of z, not y yet. So we are going to make an adjustment to that. So everywhere where there's y here becomes z. Sorry about the confusion. So we can now rewrite it in terms of z. So we have z multiplied by the integrating factor instead. We have the z over x is equal to minus x raised power minus 2 divided by 2 plus c, which you can write as minus 1 divided by 2x squared plus c. On substitution, we know that z is equal to 1 divided by y. So we can substitute this to now give 1 divided by xy is equal to minus 1 divided by 2x squared plus c. And this is the solution of our differential equation. So that concludes example number 1. Let's take another example. So the second example now. We have r sine theta minus dr d theta cos theta is equal to r squared. So we have to first express it in terms of either the linear form or the Bernoulli equation, depending on what we are given. So let's check this out. This becomes r sine theta minus r squared is equal to dr d theta cos theta. So we have dr d theta cos theta minus r sine theta is equal to minus r squared. Dividing all through by cos theta, we have dr d theta minus r sine theta divided by cos theta is equal to minus r squared divided by cos theta. So we have dr d theta minus r tan theta is equal to minus r squared cos theta. In this case, we can see that our n is also equal to 2. So dividing all through by 1 over r squared, we have 1 over r squared dr d theta minus r tan theta divided by r squared is equal to minus 1 divided by cos theta. So on simplification, we have 1 divided by r squared dr d theta minus tan theta divided by r is equal to minus 1 divided by cos theta. Now we substitute our z to be equal to 1 divided by r raised to power 2 minus 1, and that's 1 divided by r. So our dz dx is now equal to minus r raised to power minus 2 dr dx, and this becomes minus 1 divided by r squared dr dx. So dr dx is equal to minus r squared dz dx. So we can substitute this into our original equation, the Bernoulli equation we obtained. So we have 1 divided by r squared dr d theta minus tan theta divided by r is equal to minus 1 divided by cos theta. For some reason, I kept mixing the theta and the x together. So we have the z, the theta here instead of the x, the r, the theta. We also have the theta here and the theta here. So now we can substitute our values of the r, the theta, and the z theta, which we obtained before. So we have 1 over r squared. We obtained the r, the theta from here to be equal to minus r squared dz d theta. So that's what we are going to be substituting here. So this is multiplied by minus r squared dz d theta minus tan theta divided by r is equal to minus 1 divided by cos theta. So we have minus dz d theta minus tan theta divided by r is equal to minus 1 divided by cos theta. So we have dz d theta, or multiplication by minus 1, plus tan theta divided by r is equal to 1 divided by cos theta. So we can solve this using our integrating factor method. But before we do that, recall that we said z is equal to 1 over r. So we have dz d theta plus z tan theta is equal to 1 divided by cos theta. So now we have our integrating factor to be equal to e raised to power integral of tan theta d theta. So this becomes, okay, e raised to the power of integral of sin theta divided by cos theta d theta. So on evaluating this, we have e raised to power minus ln cos theta d theta. So we have our integrating factor to be equal to e raised to power ln 1 over cos theta, and that's equal to 1 over cos theta, which is equal to sec theta. There shouldn't be the theta here anymore. So now we have our solution to be z multiplied by the integrating factor is equal to integral of q multiplied by the integrating factor the theta plus c. So on substituting this, we have z sec theta is equal to integral of 1 divided by cos theta multiplied by sec theta d theta plus c. So this becomes z sec theta is equal to integral of sec squared theta d theta plus c. And when we integrate sec squared theta, we know the answer is tan theta. So we have z sec theta is equal to tan theta plus c. Now recall that z is equal to 1 over r. We can substitute this to have sec theta divided by r to be equal to tan theta plus c. So we can further simplify this by dividing through by sec theta. So we have 1 over r is equal to tan theta divided by sec theta plus c divided by sec theta. So we have 1 over r is equal to tan theta, which is sin theta divided by cos theta, multiplied by 1 divided by cos theta raised to the power of minus 1 plus c divided by 1 over cos theta. So we have 1 over r is equal to sin theta divided by cos theta multiplied by cos theta plus c cos theta. So we have r raised to power minus 1 to be equal to sin theta plus c cos theta. And this is our solution of the differential equation that we're given. We can also rewrite it as r is equal to 1 divided by sin theta plus c cos theta, which looks even more appropriate. So we'll take a final example to wrap up this section on Bernoulli equations. So for the third example, we have dy dx plus y over x ln y is equal to y divided by x squared ln y all squared. So this does not look like the regular type of equations we have been solving, but we can easily simplify it to make it look in such way. So the first thing to do is let's represent ln y to be equal to u, such that we have du dx now to be equal to 1 over y dy dx. So our dy dx now becomes y du dx. So we can rewrite our original equation to be y du dx plus y ln y divided by x is equal to y over x squared ln y all squared. Now note that ln y is equal to u, so we can write it as y du dx plus yu divided by x is equal to yu squared divided by x squared. So since y is common to everything, we can divide all through by y. So we have du dx plus u divided by x is equal to u squared divided by x squared. And now this looks like the Bernoulli equation. So the next thing is we divide all through by u squared. So we have 1 over u squared du dx is equal to u divided by xu squared is equal to 1 divided by x squared. So this is not equal to, should be plus. So plus this. So we can represent z to be equal to 1 divided by u raised to power 2 minus 1. Note that our n here is equal to 2. So and z is 1 over u raised to power n minus 1. So we have 1 all over u. Our dz dx now becomes minus u raised to power minus 2 du dx. So du dx is equal to minus u squared dz dx. We can now substitute this. So this becomes 1 over u squared multiplied by minus u squared dz dx plus u xu squared is equal to 1 over x squared. So we can go ahead to simplify this to become minus dz dx plus 1 over xu is equal to 1 over x squared. So we have dz dx, or multiplication by minus 1, minus 1 over xu is equal to 1 over x squared. Now recall that z is equal to 1 over u. So we can write this as dz dx minus z divided by x is equal to 1 divided by x squared. So we now have our general form of the first order linear differential equation. The minus here. So our integrating factor is what we have to find next. So this becomes our integrating factor now be equal to e raised to power minus integral of 1 over x dx. So our integrating factor is e raised to power minus ln x. So this becomes e raised to power ln x raised to power minus 1, and that's going to give us x raised to power minus 1, which is 1 over x. Now to obtain the solution of our differential equation, we have z multiplied by the integrating factor must be equal to the integral of q multiplied by the integrating factor with respect to x plus c. So we have z over x is equal to integral of minus 1 divided by x squared multiplied by 1 over x plus c. So we have z over x to be equal to, sorry, the x here, minus integral of 1 over x cubed dx plus c. So we have minus integral of x raised to power minus 3 with respect to x plus c. So z over x is equal to minus x raised to power minus 2 divided by minus 2 plus c. So we have x raised to power minus 2 divided by 2 plus c. So our z over x is equal to 1 divided by 2x squared plus c. Now recall that z over x is equal to 1 divided by 2x squared plus c. We now recall that z is equal to 1 over u. So we have 1 all over ux is equal to 1 over 2x squared plus c. And also recall that u is equal to ln y. So we have 1 divided by x ln y is equal to 1 divided by 2x squared plus c. And this is the solution of our differential equation. So with this, we've come to the end of this video on how to solve equations that are reducible or equations that we can convert to linear form, and is mostly called Bernoulli equations. I hope you've been able to understand the concepts and the guiding principles behind solving Bernoulli equations. So you can try your hands on many other questions. They are very, very interesting. It's a very direct method to go with. Then thank you very much for watching this video. See you next time.